A heavy snowstorm rolls in, and then you hear it. A distinct sound of thunder and see lightning sparkling in the sky. Congrats! You're one of the rare people who has witnessed thunder snow. Until recently, scientists couldn't even agree that it's a real thing. But now, as they see more and more videos of it popping up online, they're trying to understand how it forms and how dangerous it really is. One thing is for sure, if you see lightning during a snowstorm, there's at least half a foot of snow falling somewhere nearby. We can even predict heavy snowfalls by thunder snow. But it doesn't work the other way around. Not every heavy snowfall causes thunder snow, and scientists are still wondering why. They think this beautiful natural event happens in a way that's kind of similar to summer storms. Turbulence in the air makes warm, moist air near the ground rise up into the sky. As it goes up, it cools down and forms clouds filled with tiny ice crystals, supercooled water, and soft hail called graupel. When these things crash around inside the cloud, they create an electrical charge, which leads to lightning and thunder. When it's cold enough for snow, the atmosphere doesn't have as much energy as it does in the summer. That's because the ground doesn't heat up as much in the winter. So there's less warmth and moisture in the air. So there's less supercooled water in the clouds compared to a summer storm. When the right conditions do occur, it usually happens near the Great Lakes in the United States. In places like this, the cold air above mixes with the warm water from the lakes. This big difference in temperature creates areas where the air rises quickly, and those rising pockets can cause lightning and thunder during heavy lake effect snowstorms. They're also more common in the Colorado Front Range and Upper Great Plains. Another difference between thunder snow and a regular summer storm is that it's much harder to spot thunder snow. Snow absorbs sound waves, so you can only hear thunder if you're within a few miles of it. It will be more like a low rumble than a loud, sharp bang, and it's harder to see a flash of lightning against the backdrop of a bright white sky filled with flurries. This way, thunder snow can catch you off guard and strike just like any lightning. Although, lightning and thunder that come with a snowstorm are usually less frequent and less intense than those that come with summer storms. So, perhaps the worst thing that comes with thunder snow is those heavy snowfalls that can cause chaos on the roads and leave you without power for days. Another cool and rare winter weather phenomenon is the snow donut. You won't want to eat this donut as it looks like snowy wheels or tires. You can mostly find these rare natural snow shapes in the open prairies of North America or some remote places in Northern Europe. They need the perfect mix of conditions to form. First, there needs to be a layer of wet snow on the ground. The surface has to be something the wet snow can't stick to, like ice or very soft, powdery snow. Then, a strong but gentle wind or gravity on a hill has to push the snow just right. As the snow moves, it rolls up like a carpet and forms a big donut with a hole in the middle. Ever heard of the red lightning called sprites? Unlike regular lightning that strikes down from the clouds to the ground, they shoot up high into the atmosphere, about 50 miles above Earth. They're super fast, lasting just a tiny moment, so they're really hard to spot or study. Sprites happen because of a buildup of electricity in clouds, just like normal lightning. They're usually red and can look like jellyfish or carrots and get up to 30 miles wide. Pilots flying in high-altitude planes get the best views, and you can't see it from the ground. Scientists think sprites could happen on other planets with atmospheres. They tested this idea in a lab by recreating those planets' atmospheres and running electricity through them. It turned out they were right. A fall streak hole is a big circular or oval-shaped gap that sometimes appears in certain clouds. These types of clouds float high up in the sky and are often made of tiny water droplets that are colder than freezing, but they haven't frozen yet. They need ice crystals to freeze. When a plane flies through the cloud, it can bring those ice crystals into the cloud. Once they're there, the water droplets freeze quickly, get bigger, and start to fall from the cloud. This creates a hole in the cloud, and as more nearby droplets freeze, the hole gets bigger and spreads outward. A mini tornado that spins up a lot of dust and dirt on a hot day is called a dust devil. They're little whirlwinds filled with dust and debris, and they can happen all over the world. They're smaller and not as strong as tornadoes, but they can still be powerful enough to knock over small objects or lift light things into the air. In really hot desert areas, they can grow much taller and last longer, sometimes for over an hour. Dust devils form on sunny days when the ground gets super hot. Once the dust devil is spinning fast enough, it acts like a chimney, with hot air rising up and cooler air sinking down through the middle. Dust devils can be dangerous if they're strong enough, so it's best to stay out of their way. Have you ever seen a fog bow? They form in a similar way to regular colorful rainbows, but they're much wider. Fog bows are made by tiny droplets in fog or clouds instead of big raindrops like in regular rainbows, but they also appear opposite the sun. You need to look for a fog bow in a thin fog when the sun is bright. You might catch one when the sun starts to shine through the fog, or if you're near the ocean, where fog often forms. Because the water droplets in the fog are so tiny, fog bows don't have the regular bright rainbow colors. They might even look all white or faint. Some fog bows are hard to see at first because they blend into the mist, but once you spot them, they're easy to recognize. There are atmospheric rivers flowing high up in the sky. They're long, thin streams of air in the atmosphere that carry a lot of water vapor. Even though you can't see them, they sometimes hold as much water as the Mississippi River carries in one day. When these sky rivers reach land, the water vapor inside them often turns into rain or snow. Some are gentle and helpful, bringing much-needed water to dry areas. But the really big and powerful ones can cause heavy rainstorms or snowstorms. If they stop moving over certain areas, they can lead to flooding, mudslides, and other problems. One famous atmospheric river is called the Pineapple Express. It gets its name because it pulls warm, wet air all the way from tropical areas near Hawaii to places like the US West Coast. Mimetis clouds are some of the strangest and coolest ones in the sky, looking like big, fluffy pouches or bubbles. Their shape can change a lot. Some look like smooth bubbles and others stretch out like long tubes. Mimetis clouds usually form under big clouds. Inside these storm clouds, strong winds cause turbulence, which pushes air and moisture downward instead of upward like regular clouds. This creates those uneven, pouchy shapes. Because mimetis clouds are connected to powerful storm clouds, they're often a sign of bad weather, like heavy rain, hail, or lightning. In the winter, if it's cold enough, they can sometimes bring snow. Sometimes they appear with other, calmer clouds, but that's pretty rare. The best time to see mimetis clouds is when the sun is low in the sky, like at sunrise or sunset. The sunlight lights up the pouches, making them glow and look even more amazing.
Did you know that the Pleistocene era was a really important time in Earth's history? It's when the last ice age happened, and glaciers covered a lot of the planet. This period of time lasted for about 2.6 million years, and ended around 11,700 years ago. What's even cooler is that modern humans, like us, had actually evolved during this time, and had spread all over Earth before it ended. There were also some really fascinating animals that lived during the Pleistocene, like woolly mammoths and saber-toothed cats. Unfortunately, many of them went extinct at the end of this era. Earth has had some pretty wild weather patterns over the last 2.4 billion years. Although the planet is mostly ice-free, we now cycle in and out of freezing ice ages. During these glacial periods, temperatures drop, and huge areas of the planet get covered in ice. It all starts with a bit of snow, which then builds up over time. The ice reflects sunlight, making things even cooler. The result? Vast glaciers that slowly move toward the equator, changing the landscape as they go. And when the ice melts, sea levels rise again, and everything changes all over again. In total, there have been at least 5 ice ages so far. The first one was so intense that the whole planet turned into a huge snowball. Right now, we're actually in the middle of an ice age, but we're currently in a temporary warm spell that started around 11,000 years ago. These warm periods are called interglacials, and we're not quite sure how long they last. There are still massive ice sheets covering Antarctica and Greenland that hold 75% of Earth's fresh water. When these finally melt, it'll mark the end of the current ice age. Earth's temperature is affected by something called the Milankovitch cycles. Basically, the amount of heat we receive from the sun changes over years, decades, and millennia because of Earth's orbit, tilt, and axis angle. There are 3 different patterns to these cycles. The first is called eccentricity, which is all about the shape of our orbit. The second is obliquity, which has to do with the tilt of the Earth. And the third is precession, which is like a wobble as Earth spins. Depending on where we are in these cycles, we might experience colder or warmer temperatures. But other things, like the position of continents and the atmosphere, also play a role in our planet's fate. For example, our planet's orbit is not quite circular. It's actually a bit elongated, shaped almost like an egg. That means we're sometimes a little closer or farther from the sun, depending on the time of year. We call the point farthest away from the sun the apogee, and the closest point is the perigee. When we're at the apogee, we're moving away from the sun, but gravity eventually pulls us back toward it. This means our orbit changes a little each time, gradually shifting our position relative to the sun. Don't worry, even though the orbit changes over thousands of years, it doesn't have a big impact on our day-to-day lives. Changes in Earth's orbit can affect how much sunlight we get during the summer. This means that ice sheets in the northern hemisphere will melt less, and over time, they actually start to grow. As they grow, they reflect even more sunlight, which makes the climate even cooler and spreads the ice even farther. This process can last for a really long time, like 10,000 to 20,000 years, and eventually it brings the planet into its next freezing season. As for the next ice age, scientists believe it might be postponed indefinitely. They've found that our human interaction with the environment, like the use of fuels, could delay the next ice age by up to 100,000 years. Earth's past ice ages were linked to the amount of solar radiation and carbon dioxide concentration in the atmosphere, and this research can even help us predict future cycles. It's amazing to think that our actions now could affect Earth's future for thousands of years to come. And while it's not really important when the next ice age begins, it's pretty cool to know that humans have the power to shape the future on a geological timescale. Ice ages have had a huge impact on our planet and human civilization. So it's fascinating to think how our actions now might change things, maybe even for the better. What did life look like on our planet during the last ice age, though? Well, North America, for instance, was home to some huge creatures. Mammoths, saber-toothed cats, giant ground sloths, and mastodons were just a few of them. And get this, even Europe had an 11-foot tall flightless bird that weighed almost as much as a polar bear. Meanwhile, down under in Australia, there was a giant lizard that lived in all sorts of habitats during the same time period. Even though some animals from the Pleistocene era aren't around anymore, you might recognize many of those that are still around today. In Alaska, for example, you can still find brown bears, caribou, and wolves. People just like us actually lived through the Ice Age too. Our species, Homo sapiens, has been around for about 300,000 years. And we've spread all around the world since then. Some of our ancestors stayed in Africa during the Ice Age and didn't feel the full effects of the cold. and others ventured out into other parts of the world, even into the chilly glacial environments of Europe. Our early relatives, like the Neanderthals in Europe, and the mysterious Denisovians in Asia, were also around during this time. Although they seem to have gone extinct before the end of the Ice Age, it's pretty amazing to think about all those different hominids that roamed Earth during that period. What's also fascinating is how our species managed to survive the Ice Age, while some of our cousins didn't. Some experts believe that our adaptability, social and communication skills, and the use of tools played a huge role in it. And guess what? Humans didn't just hunker down during that time. We actually moved into new areas. Fossilized footprints found at White Sands National Park in New Mexico prove that humans have been in North America since at least 23,000 years ago. That's close to the peak of the last Ice Age. While a full-blown Ice Age might still be far away, there is a possibility of a mini Ice Age coming our way. Some scientists believe that in about 10 years, we might experience a significant drop in solar activity, leading to colder temperatures in the northern hemisphere. This could result in conditions similar to the Little Ice Age in the late 17th century, when the Thames River in the UK froze over. While scientists aren't quite sure what caused that cooling, it's fascinating to think about the potential changes. We've done it before, so we know that humans will most likely survive the next real Ice Age, even if we don't manage to figure out a way to stop the next freezing era. But it would come at a high cost. All the ice that would cover most of the northern hemisphere would have to come from oceans, which would cause the sea level to drop. This could mean more land for some countries, but it would also create other problems. Sea levels going down might seem like a great thing at first, but actually, it could lead to some challenges. Having been covered with salt water for thousands of years, the new land might not be very fertile. This means it wouldn't be great for growing crops, and we'd have to find other ways to feed ourselves. Back when humans first started out, there weren't many of us, and there was plenty of food. Now, with over 7 billion people on the planet, it's a different story. We'll need to be resourceful to make sure everyone has enough food to eat.
Imagine a giant, immensely powerful storm rotating over your head. You'd be terrified if you could see it. But this storm is invisible to the unaided eye. It isn't your regular hurricane. This intense phenomenon happens in space. Space hurricanes are giant swirling storms that form not in our oceans, but up in the ionosphere. It's part of Earth's upper atmosphere charged with energy from the sun. Space storms look a lot like traditional hurricanes, except they're made up of plasma, supercharged gases, and instead of raining water, they rain electrons. These massive rotating hurricanes appear over Earth's polar regions. Now, think of a space hurricane as a giant funnel or whirlpool of energy spiraling over the polar regions. It's only visible from high altitudes or by satellites. Space hurricanes also produce cyclone-like auroras. Such colorful light shows look similar to good old auroras, but there's a big twist. Space auroras usually spin near the North Pole for several hours, raining charged particles into the upper atmosphere. Hurricanes on Earth are born from warm ocean water and low-pressure areas. They're fueled by Earth's rotation and heat energy from the ocean. Space hurricanes, on the other hand, are created by a different process altogether. They're influenced by magnetic fields instead of Earth's water. When the solar wind, a steady flow of charged particles coming from the sun, comes into contact with Earth's magnetic field in just the right way, it creates a kind of swirling vortex of energy high up in the ionosphere. It starts spinning, much like how a regular hurricane spins in the atmosphere. Now, let's go all the way back to 2014. That was the first time researchers spotted a massive space storm over the Arctic using satellite data. That hurricane was huge, but at that time, they didn't know exactly what it was. What they did know was that its base stretched over 600 miles in diameter, and it had multiple spiral arms that looked just like the arms of a traditional hurricane. The storm also had a calm eye in the center. There, the plasma was still compared to the fast-rotating outer regions. Some parts of this storm spun at speeds up to 4,700 miles per hour. It's an incredible speed compared to Earth's hurricanes. The team observed the phenomenon for 8 hours. After that, it gradually broke down. Scientists managed to identify this storm as a space hurricane only in 2021, using observations that had been made several years before. Space hurricanes have several distinct features. First, it's cyclone-shaped, massive, bright auroras that can last for hours. Then there's the eye of the storm, a calm, stable center of the hurricane. A space hurricane also creates a circular magnetic field with strong disturbances around it. Plus, scientists mention electron rains in the ionosphere. These rains are what causes those bright, colorful auroras right below the storm. But how do space hurricanes form? To understand this process, we need to first talk about regular auroras, like the northern lights. The sun emits a stream of charged particles, also known as the solar wind, non-stop. And sometimes, this wind brings massive bursts of energy towards Earth. Luckily, Earth has a magnetic field that acts like a shield, protecting us from most of this high-energy solar radiation. But when solar winds are too strong, they can get into the upper atmosphere, especially near the poles. When these particles from the sun hit Earth's magnetic field, they release energy that lights up the sky in the form of auroras. Now, in a typical aurora, electrons from the solar wind excite nitrogen and oxygen molecules in the atmosphere, which then emit light, leading to colorful shows in the sky. Space hurricanes are similar, but they happen at higher latitudes, above the region where auroras usually appear. They create a swirling, cyclone-like effect that looks quite different. Scientists are still studying the exact conditions necessary for a space hurricane to occur. But they already know that, surprisingly, such storms happen during very calm space weather. This is the opposite of traditional geomagnetic storms, which need intense solar activity. Space hurricanes need just the right balance of low solar wind and northward-pointing magnetic fields. And even though these storms are uncommon, they aren't impossible, hence those unique swirling storms above the poles. When scientists observe the space hurricane over the North Pole, they notice some shocking similarities to hurricanes on Earth. Just like the typical hurricane, a space hurricane has a central area where the plasma is calm. Even more curiously, the plasma in space hurricanes spins in a counterclockwise direction, which is like hurricanes raging in the northern hemisphere. The space hurricane also has multiple spiral arms, just like the ones you can see in satellite images of Earth hurricanes. Plus, the space hurricane doesn't need the strong solar winds that typically create disturbances in our atmosphere. No, it forms in periods of calm, just like how an Earth hurricane can only form if the winds in the atmosphere aren't too disruptive. Now, space hurricanes may be high above us, but they can still affect our daily lives, especially in areas related to satellite communications and space navigation. Those electron rains caused by the storm interfere with radio signals that travel through the upper atmosphere. It can disrupt GPS systems, radio communications, and radar systems. What's even worse, this interference can impact the orbits of space debris or space junk, which is already a problem for spacecraft and satellites in low Earth orbit. The storm's electron rain slightly heats up the atmosphere, which leads to extra drag on satellites and can potentially change their orbits. At the same time, the effects space hurricanes have on Earth aren't as direct and disastrous as those of hurricanes down here. They really don't pose any serious health risks to astronauts or damaged satellites. But researchers say that studying such storms can help improve predictions for satellite operations, especially for flights that cross polar regions. Now, interestingly, scientists didn't set out to find space hurricanes when they spotted one. The discovery was a total accident. It happened when Larry Lyons, a space physicist from UCLA, and his team were looking through satellite data for another study. In this study, they noticed unusually strong plasma flows in the polar cap. the region at Earth's poles where auroras usually don't appear. When they looked more closely, they saw that this plasma wasn't just flowing, it was swirling, creating a circular pattern with a bright auroral spot in the middle. The researchers were intrigued. They analyzed over 300 different space hurricane events that happened over a span of 11 years. These storms appeared most often in the afternoon during summer months. It made the scientists believe there might be certain times and conditions that could encourage their formation. Luckily, with new research tools and techniques, scientists have been able to identify space hurricanes with greater precision. And recently, they've spotted parallel storms happening near the South Pole as well. The most exciting thing about this research is that it might help us better understand Earth's space neighborhood and the way solar energy affects it. Scientists like Lyons believe that space hurricanes may not actually be a new phenomenon. They may have been occurring for a long time, but no one noticed them. Space plasma physicists point out that space hurricanes resemble a phenomenon people observed earlier. It's called high-latitude dayside auroras. At the same time, space hurricanes are much brighter, and they have stronger circular flows, which give them those hurricane-like arms. Understanding space hurricanes could eventually help scientists predict them. It would be useful for planning space missions and making satellites more reliable. Plus, by looking at these storms, researchers hope to create a more complete picture of how auroras behave at higher latitudes. And even though space hurricanes may seem purely like scientific curiosity, they can give us important clues about how Earth's magnetic field and atmosphere interact with the solar wind. And who knows? This understanding might even help us spot similar storms on other planets with magnetic fields. It could offer clues about magnetic storms beyond Earth. Hurricanes can be a lot scarier than we often realize, especially since they can actually trigger earthquakes. This surprising and frightening phenomenon, known as storm quakes, was discovered completely by accident not too long ago. It started with scientists trying to find out more about low-frequency earthquakes. We're talking about those earthquakes that are so weak that we can't actually feel the tremor. See, beneath our feet, the Earth is constantly vibrating in subtle, unceasing ways that we can't hear or see without the right equipment. This geologic hum, so to speak, is driven by the movement of oceans, which covers about 70% of our planet's surface. Scientists have found that this hum may actually provide useful records of environmental happenings. To figure out where it's coming from, experts used equipment known as seismometers. You can think of these devices as little ears pressed to the ground. They can pick up all sorts of vibrations, like fans jumping up and down at their idol's concert, airplanes flying by, or even super distant earthquakes shaking the ground. Very low-frequency earthquakes are hard to track over long distances because the signals they produce can look different on different measuring devices. To solve this problem, experts came up with a way to track these signals by combining readings from smaller areas, kind of like putting together a puzzle. But while doing this, they stumbled upon a strange set of events that looked a bit like the earthquakes they were studying, but were not exactly the same. The first weird thing they noticed was that this specific phenomenon was seasonal. It never happened between May and August, for example. That is completely different from earthquakes, which can pretty much happen any time of the year. The second strange thing is that earthquakes usually occur more in the western part of the United States, where the ground moves along cracks in the surface. But these new strange vibrations spread not just along the west coast of North America, but also over to the east side. So what could be triggering this new phenomenon? What they surprisingly discovered is that many of these tremors coincided with the same time that massive storms hit North America. So we are essentially talking about a chain reaction. What happens is that during a specific season, hurricanes or heavy storms can transfer energy into the oceans, creating very strong waves. These waves then interact with the solid Earth, producing intense seismic activity. These bursts of energy that are born from massive storms can radiate thousands of miles across continents, leading to what we now call stormquakes. It is believed that this phenomenon can trigger earthquakes at a magnitude of up to 3.5 on the Richter scale. This means it can be felt by many people, but normally doesn't cause any damage. But that doesn't mean we can all be relaxed now, as ocean waters can indeed increase the intensity of hurricanes. Just like what happened with the frightening Hurricane Milton, which recently left a path of destruction across Florida. The blue-purplish zone you're looking at is Hurricane Milton, seen from a satellite perspective. On October 9th, this hurricane sustained winds of 155 miles per hour and lashed the region with heavy rainfall, damaging winds, and life-threatening storm surges. Estimates show that the losses could be up to $34 billion, which could make it one of the costliest storms in United States history. What happened with Hurricane Milton was pretty tricky. It all started with some record hot water in the Gulf of Mexico. That warm water acted like a power-up, giving this hurricane the energy it needed to grow. And then, there was also this process called eye wall replacement that helped it get bigger too. We'll get to that in a moment. So as Hurricane Milton approached the coast, something unusual happened. It crossed paths with a fast-moving air current called the jet stream, which flows high up in the atmosphere. Now normally, the winds in the northern and northwest parts of a hurricane are not as strong as those in other areas. But because of this interaction with the jet stream, the winds in these parts of the storm became much stronger than expected. At nearly every turn, Hurricane Milton surprised everyone and intensified faster than we have seen in ages. It threatened to slam both Florida's west and east coasts with a dangerous surge of water, putting the bustling area of Tampa Bay, which is home to over 3 million people, at serious risk. So how did Milton become such a major problem? Well, the problem started in the eastern Pacific Ocean. Usually, hurricanes follow a fairly predictable path, spinning off of Africa's coast, sailing across the Atlantic, and gaining strength in the warm Caribbean waters. But Milton had a twist in its origin story. It began as the remnants of a tropical depression that crossed over the Yucatan Peninsula and met a stalled front in the Gulf. Once Milton got going, it didn't hold back. But when it hit those record-high ocean temperatures, it was like giving it an energy drink. The warm water and humid air were the perfect ingredients for a hurricane on the rise. Quickly, Milton's wind speeds increased by 92 miles per hour. So it went from a tropical storm to a Category 5 hurricane in less than 2 days, which is basically insane and off the charts. And if that wasn't enough, Hurricane Milton also went through this thing called eye wall replacement. Now, hurricanes spin around a mostly clear eye in the center. But overnight, Milton started forming new bands of rain on its outer edges, creating a second ring around its eye. This process helped Milton grow even bigger, spreading out the wind speeds and giving it a larger footprint. It's kind of like shedding its skin and getting ready to become even more powerful. Hurricane Milton also had this little wobble in its path, which changed where it was heading. You can think of it like a spinning top that gets nudged and wobbles a bit before finding its balance again. That wobble meant some areas could get either hit hard or be spared from the worst of the storm. Thankfully, Hurricane Milton weakened a bit because of some tricky wind changes up in the atmosphere until it finally made landfall. After that, it moved across the peninsula and headed out to sea, quickly losing strength as it pulled away from the warmer waters. Now, even though the damage was significant, the good news, if you can call it that, is that experts were honestly expecting things to be way worse. Still, it raises a question. How close was Milton's wind speed to the maximum? Or, in other words, is there a limit to how strong a hurricane can get? Well, the answer is yes, there is a speed limit for hurricane winds, but it's not a set number. Right now, the strongest the storm can get is around 200 miles per hour. But that maximum speed can change depending on many factors, like the heat in the ocean. Think of the ocean as the fuel for hurricanes. The warmer the water, the more fuel these storms have to work with. Experts believe that as the oceans continue to warm, they can ramp up the wind speeds and the impacts of hurricanes, making them a lot stronger. But other things can also help figure out how intense a hurricane can get. For example, the heat in the air and the temperature at the top of the clouds matter, as they also affect how fast heat moves from the ocean surface to the top of the storm. Some estimates suggest that maximum wind speeds could reach closer to 220 miles per hour until the end of the century. So it's definitely something that experts need to keep an eye on to help prevent future disasters. As we move forward, it's essential to keep researching and studying these storms. The more we understand them, the better we can protect ourselves and our communities.
Hey, want to take a wild trip back in time to the Jurassic or Cambrian era? Trust me, it's going to be a wild ride, but surviving in those ancient environments would require some serious skills. At the start of the Cambrian era, the air would be as thin as at the base camp of Mount Everest, but the climate was actually pretty chill and consistent back then. However, there was one teeny tiny problem: no land plants or animals to feast on. So forget about firing up the grill for a juicy steak. Instead, you'd have to come up with creative ways to catch trilobites and other funky-looking shellfish. Good luck finding a spear without any wood or a fishing net without any plant fibers. And get ready to eat them raw, unless you can figure out how to extract oil from these creatures or burn dry seaweed. But wait, if you're looking for a more comfortable existence, you gotta travel to 100 million years ago, to the Silurian period. Here, things start to get a bit easier. The air is still thin, but there's a bit more oxygen to go around. Plus, the climate is warmer and cozier. Simple land plants have finally made their debut. Not only that, but the first bony fish also show up on the scene, so you might actually find something more palatable to munch on. Just watch out for those prehistoric millipedes and spider-like creatures that share the land with you. They might not be the best dinner companions. Yeah, it all sounds fun and feasible, but let's talk a bit more about this crazy idea of instant transportation. If you magically appeared in a different time, the first thing you'd have to worry about is the amount of oxygen in the air. Now, looking at that fancy graph up there, it's pretty clear that oxygen levels used to be super low before about 0.85 billion years ago. Like, we're talking just a few percent of the atmosphere. And there wasn't even any O2 in the air until this event called the Great Oxygenation happened about 2.3 billion years ago. So if you ended up back then, surviving would totally depend on how fit you are. If the oxygen concentration was less than 10%, you'd probably pass out, but not pass away. If it was just above 10%, you might be able to function, but you wouldn't exactly be living your best life. Based on oxygen alone, it seems like you could survive if you showed up around 0.75 billion years ago, give or take a few million years. Now let's talk about the cool stuff on land. The first land plants didn't show up until around 450 million years ago during the Ordovician period. Before that, there were some large algae hanging around, mostly in the range of 500 to 600 million years ago. But there wasn't a whole lot going on until those land plants came along. Other forms of life didn't start showing up on land until closer to 300 to 400 million years ago. But there was this critter, a myriapod, that lived around 428 million years ago, and it was one of the earliest land dwellers. I mean, if you lived back then, you'd have to come up with fancy recipes featuring myriapods. Not exactly mouth-watering. Don't worry if you find yourself back in time before all that land action. Around 500 to 600 million years ago, the oceans were teeming with life. There were these creatures called the Edicarian fauna, and they were some of the first well-preserved organisms. Some of them probably hung out in the shallow areas near the shore, so you might be able to get your hands on them for a meal. But remember, there weren't any land plants yet, so you'd probably have to eat them raw and with no potatoes on the side. You'd have a sort of prehistoric sashimi on your plate. Now, around 500 million years ago, things started to get really interesting in the oceans after something called the Cambrian explosion. If you ended up in the Cambrian period, you'd have all sorts of weird animals to catch in the coastal zones. Check out the fossils from the Burgess Shale for some wild ideas. Look at these brachiopods, arthropods, and even worm-like critters. But again, no woody land plants at this point, so your meals would mostly consist of raw arthropods and algae. Alrighty, let's dive into the nitty-gritty of ice ages. It's when the Earth gets super chilly for a ridiculously long time,
like millions and millions of years. This causes giant ice sheets and glaciers to spread all over the place, covering massive areas of the planet's surface. Believe it or not, our planet has experienced at least 5 major ice ages. The very first one happened about 2 billion years ago and lasted for 300 million years. The most recent ice age kicked off at around 2.6 million years ago, and we're technically still in it. So, we're in the middle of an ice age, but we're not currently living in an icy wonderland. That's because we're currently in an interglacial period. During an ice age, temperatures go through ups and downs. When it's warmer, those ice sheets and glaciers start to melt, creating what we call interglacials. And when it gets colder, they expand again, which we call glacials. So right now, we're enjoying the warm interglacial period of the most recent ice age, which kicked off around 11,000 years ago. When people mention the ice age, they're usually talking about the last glacial period that started around 115,000 years ago and ended roughly 11,000 years ago when our current interglacial period began. During that glacial period, things were way cooler than they are now. At its peak, when ice sheets covered most of North America, the average global temperature was about 46 degrees Fahrenheit. That's a whole 11 degrees Fahrenheit cooler than today's global average temperature. That temperature difference may not seem like much, but it was enough to turn most of North America and Eurasia into ice-covered landscapes. The Earth was also a lot drier, and sea levels were way lower because most of the water was trapped in those ice sheets. We're talking vast steppes, dry, grassy plains as far as the eye can see. And let's not forget about the savannas, warm, grassy plains, and deserts that were also part of the icy scene. During the Ice Age, there were some familiar critters roaming around, like brown bears, caribou, and wolves. But there were also some mega cool creatures that sadly went extinct when the Ice Age came to an end. We're talking mammoths, mastodons, saber-toothed cats, and giant ground sloths. Now, there are a bunch of theories floating around about why these magnificent beasts bit the dust. One idea is that us humans hunted them into extinction when we crossed paths with these megafauna. Our species, Homo sapiens, actually survived the Ice Age. We've been kicking it on this planet for around 300,000 years now, starting out in Africa and then spreading our awesomeness all over the globe. Some of our ancestors stayed put in Africa and didn't experience the full icy effects. Others ventured into different parts of the world, even braving the freezing cold of Europe's glacial environments. But we weren't the only ones out there. At the beginning of the Ice Age, there were other hominids, our closer relatives, scattered across Eurasia. We had the Neanderthals chilling in Europe, and the mysterious Denisovans hanging out in Asia. Sadly, both of these groups seems to have vanished before the Ice Age wrapped up. Now, there are countless theories about how our species managed to survive the Ice Age while our hominin buddies didn't make it. Some believe it's because we're ridiculously adaptable and used our social skills, communication, and nifty tools to our advantage. And get this, humans didn't just hunker down during the Ice Age. Nope, we explored new territories and made ourselves at home. For the longest time, folks thought humans didn't set foot in North America until after the ice sheets started melting. Fossilized footprints discovered at White Sands National Park in New Mexico prove that humans have been rocking it in North America for at least 23,000 years, right around the peak of the last Ice Age.
Around 2,500 years ago, an earthquake completely changed the course of one of the largest and most famous rivers on the planet, the Ganges. Now, it's normal for rivers not to sit in one place, so if you live next to one, it could also just disappear without a trace or flood the whole city one day. In the case of the Ganges River, a supermassive earthquake became the reason for this dramatic change. Scientists say it might happen again, and it would be a huge problem for millions of people who depend on this river. The Ganges River starts as small streams in the Himalayas and travels a long way, over 1,500 miles. Along its journey, it meets other big rivers before all the water flows into the Bay of Bengal. The Ganges has the largest delta in the world among all rivers. Just like many other rivers in the region, it slowly changes its path over time. These changes, if they happen when a river wears away its banks, usually takes a long time, sometimes decades. Scientists have discovered that the Ganges-Brahmaputra river system has shifted several times over the last 6,000 years. When they looked at satellite images of the Ganges Delta, they noticed something interesting. There was a crescent-shaped dip in the ground about 28 miles away from where the river is flowing now. This depression was over 1 mile wide and stretched for many miles. They thought it might have been an old main channel of the Ganges River a long time ago. In 2018, the team decided to visit the area to check it out for themselves and take samples to learn more about it. While driving back home, they noticed a pit where someone was digging dirt to create a pond. The next day, they planned to fill it with water, but the researchers spotted something strange in the dirt. There were vertical bands of light-colored sand mixed into the darker mud. These special layers are clues from the past. They show that an ancient earthquake made sand and water shoot up from below the ground and created sand volcanoes that were trapped in time. The scientists studied the sand and mud and figured out that these earthquakes happened around 2,500 years ago and were strong, with magnitudes of 7 to 8. The epicenter was over 110 miles away from the main stem of the river, but it was powerful enough to displace it. It could have affected around 140 million people. The Ganges-Brahmaputra system is close to spots where Earth's tectonic plates meet, so earthquakes happen here often. There's no danger right now, but scientists think that another massive earthquake could happen in the next few hundred or thousand years. It could threaten up to 170 million people. That's about half the population of the U.S. No one can predict exactly when an earthquake will happen or how strong it will be. Learning how earthquakes in the past moved rivers helps scientists figure out patterns and make guesses about similar events in the future. This knowledge could help us prepare better and create safety plans before another big earthquake strikes. Now, the Ganges isn't the only river at risk. The Yellow River, the Irrawaddy River, and rivers in the United States like the Klamath and San Joaquin all face similar dangers. The mighty Mississippi River has also switched its path many times over the last 7,000 years. Right now, there's a huge system of dams and barriers called a control structure in central Louisiana. This structure's job is to stop the Mississippi from spilling over its banks and joining a nearby river. But scientists think that, in theory, these barriers wouldn't handle megafloods. So the Mississippi could break free and change its course again. This would cause massive problems, especially in southern Louisiana. One of the recent examples when a river changing its course caused disaster was the Kosi River in India. In August 2008, over just a few days, the river's path shifted by almost 60 miles, which is a huge change. Floods happen in some parts of the state rather often, but they hadn't seen such strong ones in over 50 years. They affected around 1,000 villages and 3 million people, and about 1 million people had to be evacuated to safety. Since many of these people hadn't faced floods in so long, they weren't ready to handle it quickly. It caused even more damage to their homes and lives. Scientists have been trying for decades to figure out what exactly makes rivers suddenly change their course. A new study explains that two things work together to make a river to do it. This process is called avulsion. First, there's the setup, which is like building up tension before something big happens. Over time, sediment, sand, dirt, and other stuff carried by the river gets deposited in certain places. It either raises the river above the land around it or makes a nearby slope steeper than the river's current path. Then there's the trigger, which is like the final straw that makes everything happen. This trigger could be a big flood, an earthquake, or even something like a pile of logs blocking the water. Now, researchers looked at satellite images of about 170 cases of avulsion from the past 50 years. They noticed these events happen most often near river mouths and near mountains. Rivers were about 3 times more likely to change course in these places than in the areas between them. They also studied 58 river channels in detail, using super clear maps to measure super elevation, That's how high the river is compared to the land around it. They also measured slope advantage. That's how steep a new path might be compared to the river's current one. They found that near mountains, rivers often pile up so much sediment that they become super elevated and spill over. But near river mouths, like in deltas, rivers need a steep slope advantage to break through the mud and form a new path. These two factors work together like a seesaw. If one is stronger, the other doesn't need to be as strong for an avulsion to happen. To figure out where a river might go if it changes course, the researchers created a smart computer algorithm. This tool uses maps to measure the terrain's steepness and the river's flow to predict where the river might move. They tested it on 10 past avulsions, and it correctly guessed the path every single time. Scientists hope they could use these findings to protect people living near rivers from sudden floods. Rivers changing course played a big role in creating one of the first organized administration systems in the world. Scientists found clues for this in the territory of ancient Mesopotamia. This name means the land between two rivers, and it was between the rivers Tigris and the Euphrates. People living there relied on these rivers for water, food, and transportation. Scientists wanted to figure out how these sudden changes in these rivers affected ancient people. To do this, they used two kinds of maps. The archaeological maps show how ancient cities grew over time, including what types of buildings people built. Certain buildings, like big palaces or city walls, could show when each city first had an organized administration. The second kind of map showed where the Tigris and Euphrates rivers flowed long ago. They often shifted, sometimes slowly, and sometimes very quickly and dramatically. Around the year 5000 BCE, Mesopotamia started to become drier and farming became harder. Farmers had to grow their crops near rivers, where they could use the natural floods to water their fields or dig little channels to bring river water to their plants. Because farming was so important, towns and cities grew near the rivers too, so people could stay close to their food. But when a river suddenly changed its course, people didn't give up. They worked together to dig long canals to bring water from the new river path back to their fields. The canals helped them get water again, and the administration buildings showed they were organizing as a community to solve big problems together.
The snowpack over your head splits in two right in front of your eyes and starts tumbling down in the frozen slope to its resting place far, far below. Anything in its way is crushed under the immense mass of snow and debris. You're witnessing an avalanche, one of the most dangerous natural disasters. But what if I tell you about another kind of avalanche, no less blood-chilling than the mountain one? And the most bizarre thing about it is that it occurs underwater. Underwater avalanches are powerful and disastrous natural phenomena, often much more dangerous than land ones. They have the potential to wreak havoc on the entire planet, leading to catastrophic consequences. The most alarming thing? They occur all the time under the surface of the ocean, impossible to see, predict, and extremely difficult to measure. Such avalanches can get 100 times larger than land ones, and they pose a great risk to the world's communications, capable of leaving the entire planet without the internet. But we'll talk about it a bit later. First, let's go 60,000 years back into the past. We're near the northwest coast of Africa, ready to witness the colossal scale and devastating impact of a ginormous underwater avalanche. It started as a quite small underwater landslide in the Agadir Canyon. At first, it was just 0.35 cubic miles of material, but in no time, this mass increased more than 100 times in size while traveling across the Atlantic Ocean floor. As the avalanche sped up and grew, it picked up gravel, sand, rocks, and mud. It carved a devastating path through one of the world's largest submarine canyons, wiping out all forms of animal and plant life on its way. The disastrous flow was so powerful that it literally eroded a 250-mile stretch of the canyon, cutting hundreds of feet into its sides and damaging a total area of 1,740 square miles. That's the area of more than 3.5 New York cities. As for the force of the flow, it was so immense that it propelled massive boulders up the canyon walls to heights of up to 430 feet. Before scientists discovered the evidence of this catastrophic event, they had seriously underestimated the scale of destruction caused by submarine avalanches. By the way, these devastating catastrophes can start not only far away in the ocean, but also at estuaries. Let's go back to 14 January 2020 and see for ourselves. A turbidity current, a rapid, downhill flow of water containing a lot of sediment, rushed more than 680 miles from the Congo River estuary in the deep sea. This current appeared due to two factors: terrible flooding along the Congo River in late December 2019 and unusually large spring tides. This resulted in an avalanche of sand and mud. Its volume was equivalent to 1/3 of all the sediment produced annually by all the rivers in the world. This sediment avalanche accelerated, increasing in speed from 17 feet per second in the upper part of the Congo Canyon to 26 feet per second when it reached the end of the channel, almost 700 miles away from the coastline. This route made it the longest avalanche of sediment ever measured on our planet. 2 days later, the flow reached the deep ocean. The avalanche broke 2 seabed telecommunication cables, cutting internet data speeds all the way across West, Central, and South Africa. Now, before this disaster, scientists considered that measuring powerful deep-sea avalanches was impractical. But the sediment flow in the Congo Canyon could be monitored directly, finally allowing researchers to assess how major river floods connected to the deep sea. They also concluded that how often underwater avalanches occurred depended on where the observer was. Seafloor canyons that are close to river mouths can experience several tiny avalanches per year. Other systems, far from river discharges like the Agadir Canyon, can only have one monster of an avalanche every 10,000 years or so. You're likely wondering, what can trigger an avalanche under the surface of the ocean? Well, earthquakes, typhoons, high tides, river floods, and even volcanic eruptions. And due to our changing climate, such events become more and more frequent and intense. At the same time, these triggers don't mean that an avalanche is bound to happen, nor do they relate to the scale of the event. See for yourself. In 1755, a powerful earthquake hit the coast of Portugal, wiping out large parts of Lisbon. Tens of thousands of people lost their lives during that disaster, but it only triggered a tiny underwater avalanche. And in 1929, a large earthquake off the coast of Newfoundland, Canada, triggered the largest underwater avalanche ever recorded. The flow traveled at a speed of 42 miles per hour, carrying boulders, sand, and mud. It snapped 11 seabed cables on its journey downhill. The avalanche was so powerful, it produced a tsunami that claimed the lives of 28 people along the coastline. Now, submarine avalanches are totally invisible because they happen deep under the ocean surface, which makes them extremely hard to study. But we must find a way because these flows are super important. They transport sediments, nutrients, and even pollutants across the ocean floor. So, a research team from Liverpool decided to unravel this mystery. Over the last 40 years, they've collected more than 300 samples from the ocean floor. Combined with seismic and bathymetric data, which is a fancy word for ocean mapping, they managed to reconstruct a massive submarine avalanche. It was the first time an underwater avalanche of this size was mapped out. An even cooler thing, the event itself started off pretty modestly, but it quickly evolved into a colossal avalanche that grew to more than 650 feet tall. To put that into perspective, imagine a skyscraper-sized avalanche zooming from Liverpool to London, cutting a trench 100 feet deep and 9 miles wide. Then it spread out over an area bigger than the UK, covering it with several feet of sand and mud. That's like burying a whole country. These findings are actually a big deal because they show that even a small underwater landslide can turn into something massive and super destructive. But that's not the worst. Think about undersea internet cables. which are essential for global communication. There are more than 550 active seafloor cables around the world. Their combined length is a whopping 870,000 miles. That's enough to wrap around our planet 35 times. When a submarine avalanche breaks seafloor cables, the effects are usually super expensive and devastating. For example, in 2006, an earthquake in Taiwan triggered underwater avalanches that cut loads of seafloor cables connecting Southeast Asia with the rest of the world. The largest internet operator in China had a 90% loss of traffic to the USA at the peak of the event. As for Taiwan itself, it experienced between 74 to 100% loss in traffic to neighboring islands. So now you probably get why we need to learn more about this natural phenomenon. Luckily, researchers at Tulane University have found a way to study it in 3D. Previous studies only looked at submarine avalanches in 2D, which didn't give the full picture of how they actually behaved. The new research focused on how underwater flows interacted with mini basins, natural features on the ocean floor that look like shallow bowls. Despite being called mini, these bowls can be huge, up to 4 square miles. When turbidity currents flow into these mini basins, they don't just stop. No, they hit the far side and curl back around like water eddies in a stream. These swirling flows move the sediment around before it settles on the ocean floor. The size of the mini basin and the speed of the flow can change how the current behaves. If the basin is big and the current is slow, it starts to fill up with sediment. But if you crank up the flow speed or shrink the basin, the current starts to overflow, spilling over the basin. To study all this, the researchers created a mini version of a mini basin in a pool and used different speeds of flow to simulate turbidity currents. They even made their own sediment mixtures to see how different sizes of particles would behave. In the end, they managed to mimic real-life ocean conditions, but on a smaller, manageable scale. Pretty cool, huh? Back in the day, from 774 to 775, Earth got hit with a mega blast of radiation. This crazy burst of energy left its mark. 3 rings from that year show way too high levels of radioactive stuff. But what exactly caused it? Scientists are inclined to think that the reason was a solar flare. Some folks think maybe a massive supernova caused the radiation blast. But astronomer Phil Plait says that if that had been the case, it would have had to be less than 1,000 light years away and would have been crazy bright. But there's no record of that happening. No bright, shiny Death Star in sight. After looking at the radioactive carbon and beryllium in tree rings, scientists ruled out a bunch of other possibilities. At first, they considered that it was a smash-up between neutron stars or a neutron star and a black hole. These types of crashes produce a super quick blast of gamma rays without any light show, which lines up best with the evidence. But these kinds of collisions are super rare. Plait thinks it's kinda unlikely that this is the answer. He figures we should only see one of these events in our galaxy about once every million years. So having one just 1,200 years ago seems pretty wild. Scientists are seriously worried about these rare events. If one happened closer to Earth, it could seriously mess up life on our planet. Even if it was thousands of light years away, a similar event today could cause chaos with all the fancy electronic systems we've come to rely on. So it's a good thing those gamma ray bursts are so rare, because if they were more common, Earth might be in for a rough ride. You may think that if our planet could withstand mega radiation blasts, it can easily withstand something less frightening. Let's say grasshoppers. Sorry to say that, but it's not exactly true. Back in 1874, during a hot summer in Kansas, things took a strange turn. Grasshoppers, or should I say locusts, invaded the Great Plains like nobody's business. They came down like a storm, blanketing houses, trees, and even poor trains passing by. These bugs were on a mission to cause chaos. Farmers had to scramble to protect their wells and just about anything else worth saving. Locusts landed everywhere, wreaking havoc on everything in sight. Even poor sheep lost their wool Locusts even stripped paint off wagons and handles off pitchforks. This is how destructive they were. Livestock tried to fight back by eating them, but there were just too many of these insects. That year, those critters caused about $200 million in crop damage. The locust invasion was so tough, even the US Army stepped in to help. In the end, locusts began to disappear, sparing the plains from further devastation. Natural disasters can be even more unexpected than radiation blasts from space and locust invasions. Check this out. Back in June 2017, a reindeer herder up in northwest Siberia was minding their own business when they suddenly heard a crazy loud blast and saw smoke shooting up from the ground. If that happened to me, I'd need to change my pants. Sorry. Later on, they found this huge hole that was like 23 feet wide and nearly 65 feet deep and was surrounded by chunks of ice and dirt. It turned out that there were over 17 such black holes in the area. They were filled with peaty water and shrouded in mystery. Some folks thought those were sinkholes. Others were sure they were left by top-secret device tests or even a bunch of meteorites. Now, the latest idea is that these holes are actually craters caused by the Arctic warming up and melting the frozen ground. The theory states that as the ground thaws, gas pockets trapped beneath the surface burst through, creating such dramatic holes. Apparently, these eerie craters have been showing up in specific spots in Siberia where ancient geological faults have been leaking out hot natural gas for ages. Combine that with some leftover methane from old lake sediments, and you've got a recipe for some explosive surprises as the planet heats up. Not scared yet? All right, maybe you're afraid of darkness, huh? If so, you wouldn't like it back in 536. It's the year when the world went through a crazy 18-month period of darkness. A mysterious fog covered Europe, the Middle East, and parts of Asia, blocking out the sun and causing chaos. It was like the Dark Ages, but for real. It turns out that the main culprit behind this fog was a volcanic eruption in Iceland. This eruption spread ash across the northern hemisphere, causing temperatures to drop and crops to fail. People were freezing and starving. It was a mess. Historians from back in the day even talked about how weird it was. The sun looked like the moon, summers were freezing cold, and even China had summer snow. It was all because of the volcanic ash blocking out the sun. And to make things even worse, this period of darkness sparked the beginning of the bubonic plague in 541. Talk about a rough time to be alive. Let's go back to Siberia real quick. Back in 1908, way out in the wilds of Siberia, an asteroid dropped for an unexpected visit. Today, we know it as the Tunguska asteroid, but it didn't get its name instantly. Local folks only caught a glimpse of the show. A bright fireball streaking across the sky, followed by a massive boom. Trees went flying, fires blazed, and animals weren't too happy about it either. But since the area was so remote, not many folks took notice. For almost 2 decades, nobody bothered to check out the Tunguska site. People had too much on their plates back then. But then, scientists finally made it out there and found evidence of the asteroid's shenanigans. Later in expeditions, they found some spacey microparticles. Fast forward to now, and NASA has a whole planetary defense thing going on. They even sent a mission to test out asteroid deflecting tech. Because who knows when the next cosmic rock will come knocking on our door, right? In the middle of the 19th century, there was one more epic solar storm called the Carrington event. It may not sound like a big deal to you, but it had pretty rough consequences. The next day after the storm, Earth was hit with this insane geomagnetic storm that threw telegraphs off the rails and brought auroras to the tropics. And it's the place where they normally never show up. Turns out, all this space weather madness started with weird stuff happening on the sun's surface, like sunspots. From these spots, solar flares and other crazy electromagnetic stuff can pop out and mess with our technology. Massive solar storms like this one can shoot out from the sun at speeds of up to 1,800 miles per second. They can contain billions of tons of solar material, complete with a sassy little magnetic field that loves to mess with Earth's magnetic field when they meet. Now, listen closely. We're getting close to the next solar maximum in 2025, so it's a good time to check out the history of the worst solar storms, like the Carrington event, and take notice. Imagine if a similar storm hit today. An internet apocalypse, anyone? Businesses would be sent offline and we'd be facing some serious damages. Luckily, these mega solar storms don't happen very often. But hey, space weather is tricky to predict, so who knows when the next one will hit?
Rocks rolling down the slopes of a rumbling volcano, pushing other bigger rocks on their way, and eventually tumbling down into the ocean in a humongous cascade, causing a wave the height of which the world's never seen before. This is what might happen if the Helena slump of the Hawaiian Big Island falls off into the water. The Kilauea volcano is far from dormant. The latest eruption occurred in 2018. Its eruptions are usually accompanied by earthquakes of different magnitudes, and with each quake, the magma rocks on the slopes of the volcano shift down. These rock formations are called slumps, and the Helena slump is the most notorious of them all. In 1868, the shift of this slump caused a tidal wave rising as tall as 60 feet. But what's most troubling is that some 110,000 years ago, a landslide here led to one of the most powerful earthquakes ever, which in turn led to a mega tsunami of over 1,000 feet in height. Scientists are worried that such an event may repeat in the future. If that happens, the wave might engulf the whole of Hawaii and easily reach both North and South American coasts. Geologists are quick to reassure, though, that a landslide like this is unlikely to occur anytime soon. It's just too early for that. But when it finally does, the consequences will be catastrophic. Have a nice day! Yellowstone National Park in the western USA is world famous for its dazzling views, and especially the colorful Grand Prismatic Spring at its very heart. But we should all stay aware that Yellowstone is, first and foremost, an enormous caldera, basically a slumbering supervolcano. The difference between a regular volcano, like Kilauea from earlier, and a supervolcano is that the latter is thousands of times more powerful. Imagine an eruption spewing tons of huge rock and rivers of hot lava, pumping out clouds of ash that make countries stop air travel for weeks. And now multiply all of this by 1,000. This is what a Yellowstone eruption would look like. At first, a huge area in the middle of the national park would shake, crumble, and then blast upwards in a megaton explosion. Lava flows and magma rocks would cover the area of about 40 square miles, roughly half of Washington, D.C. But the greatest danger is the volcanic ash. The ashen plume would rise miles above and get carried by the wind in every direction. Since the eruption would be far from ordinary, the spread and damage would also be much greater than usual. The ash is thick and heavy, so it would cover a vast area in a blanket, destroying crops and even buildings. Worse still, it would spread in the air and block out the sun, leading to a drastic drop in temperature and an artificial winter. Even regular volcanoes can lower temperatures worldwide by a few degrees. A supervolcano may potentially cause a new ice age. Luckily, the chances of Yellowstone supervolcano erupting in the near future, or at all, are extremely low. There have been only 3 of those in the history of Earth, and there's no evidence such a disaster should repeat. Scientists estimate the probability at 0.00014%, which is lower than the chances of an asteroid wiping us all out. Speaking of which, if dinosaurs could talk, and were at least still alive for that matter, they'd tell you that asteroid threat is as real as it gets. Scientists at NASA say they've tracked 90% of all near-Earth asteroids of significant size, and none of them are a matter of any concern. But there are still the other 10% in the great unknown. What's more, asteroids can change their line of flight because of the pull of other celestial bodies and eventually turn our way. Lucky us! Now, if an asteroid big enough, like a mile across, hits the Earth, It will first cause an explosion powerful enough to erase a dozen big cities in a matter of seconds. Then the impact will raise a cloud of dust and debris that will block out the sun, just like the ash cloud from a volcano, and cause a centuries-long winter on the whole planet. But even if it falls into the ocean, which is more likely, a resulting wave will rise several miles high, washing coastal cities off the face of the planet. But at least there won't be a new ice age. Although scientists are pretty sure there's no such threat in the near future, it can't be ruled out completely, and humanity needs at least 5 years to prepare for this event. If a big near-Earth asteroid suddenly changes its course and turns right toward our planet, we won't stand a chance against it. Disaster movie, anyone? A much more probable calamity, though, rests right beneath our feet. It's the San Andreas Fault in California. The fault has been ready for rupture for years now, and scientists estimate that an earthquake along this line is likely to occur in the next 3 decades. And when it happens, it won't be nice. They expect a magnitude of 8.0, which is comparable to some of the most devastating quakes in history. It's all the more dangerous since California is home to some of the most populated cities in the western U.S., including Los Angeles and San Francisco. High-rise buildings are common there, and they're particularly vulnerable against underground shakes. The San Andreas earthquake might cause a whole lot of damage both to cities and countryside. In the worst-case scenario, the ground might break apart, destroying buildings, farms, and changing the landscape altogether. Still, scientists believe that the probability of such a quake is only 7% for the next 30 years. So, there's a rather big chance, 93%, that we'll never see that in our lifetime. Yet, there's another earthquake hazard not so far away from the previous one: the megathrust in Chile. The country sits right above the subduction zone, an area where 2 tectonic plates meet and go one beneath the other. At the place of their meeting, stress has accumulated because of their continuous movement, and once that strain is too much, a major earthquake occurs. Chile has experienced a lot of quakes in the recent years, and scientists are worried those might be preparing the area for a really big one. They believe a great earthquake is due to happen before the end of the century, and it might be devastating to the coastal area. Even smaller quakes caused tsunamis that flooded the west coast, and a huge one like that is likely to raise a wave of incredible height. On the bright side, Chile now knows to prepare in advance for the coming natural disasters, and geologists are pretty sure people will be able to evacuate before the earthquake strikes. In September of 1859, astronomer Richard Carrington was looking at the sun and suddenly saw a bright flare on its surface. He made a note of it in his records, but only realized how important it was a couple of days later. The energy from that flare reached Earth and struck it directly, causing northern lights to appear above Cuba and burning telegraph lines all around the world. This was dubbed the Carrington event, and it was a solar storm. Such storms hit the Earth fairly often, but none of them were so powerful as the Carrington event, neither before nor after. But in 2012, astronomers registered a similar solar flare whose energy nearly hit our planet once again. If it had been just a week earlier, we'd have been in big trouble. Today, humanity relies on electricity in almost every aspect of life, and a powerful solar storm would mess with the electromagnetic field of Earth a lot. All electric appliances would either shut down or short-circuit, and huge transformers powering basically everything would go out of order for good. It would take years to repair them, and the cost of such a massive blackout would count in trillions of dollars. The worst of it is that science is almost unable to predict solar storms, and even if we could know about them in advance, we'd be powerless to stop them. The flare happens in a matter of seconds, and it takes about 8 minutes for the particles to reach the Earth's atmosphere, causing the disturbance. The power outage would come a bit later, in a day or so, when a massive cloud of plasma gets to our planet. At the moment, there's no protection against solar flares, and the chances of one powerful enough to cut all of our electricity in the next few years are quite high, about 12%. The only good thing about all this is that we now know of such a possibility and can at least prepare in advance. Hey, don't forget to pack some underwear and socks. You'll always need those.